reducing fractions up to this point has been finding what you can commonly pull out of both the numerator and the denominator until you get to a point where there's nothing other than a 1 that can be pulled out. Okay, so take for example, this is my example 1. And in nowadays they don't say reduce, they say simplify. Take for example 24 over 36. If you wanted to reduce this, you would divide both pieces by the greatest common factor of both components. Would you agree with me that that's the process? It might be not be how you word it in your brain, but it is what you're doing. In the end, when you divide out 12 over 12, you get 2/3, right? And that's simple. Those are tiny fractions. Those are fractions that you could do at the top of your head. You wouldn't have a problem with doing it that way. Another way that some people have to do these because they simply can't visualize greatest common factors, and I'm using something really, really simple, so bear with me, is they prime factor the numbers. Again, this is super simple, but I'm going to go through the process anyway so you can see how valuable it can be. Okay, there's 24, and I'll finish up 36. Okay, 3, 3, 3, good, right? Okay, so the prime factorization of the number 24 is 2 times 2 times 2 times 3. And the prime factorization of number 36 in the denominator position is 2 times 2 times 3 times 3. Wherever a pair exists. Now, it doesn't mean they match each other location-wise. Like I can say these 2's match one another. Doesn't matter that those two 2's are not stacked. It's the fact that there is a match. In the same way that these 2 match. And when they match, what they're doing is becoming a 1. 2 divided by 2 is 1. 2 divided by 2 is 1. And I'm going to do these 2 3's just to continue to buck the trend of them being on top of each other. So the numerator is now 1 times 1 times 2 times 1, which is 2. And 1 times 1 times 1 times 3, which is 3. So in effect, this long drawn out process is simply us identifying where the top and bottom matches. And incidentally, if you go 2 times 2 times 3, what do you get? 2 times 2 times 3? Good. And that's exactly what we pulled out. So in the end, and this is going to look confusing, this is the rule that is listed in like the second gray box. If you have a fraction and you could pull the same thing out of the top and the bottom, the result is what's left. The B's here represents the 12 up there. And if I rewrite it, 12 times 2, 12 times 3, indeed, we did find that it does equal 2/3. And that big, busy description is going to prove invaluable to you when you get to a place where things are a little tougher. So bear with me. I know right now you're thinking I'm wasting your time, but I'm really not. Example 2, I'm going to just do a couple more. There isn't much different going on here, but we're going to practice a couple more anyway, and I can squeeze these in. Example 2, 15 over 20. So 15 is 3 times 5, if I wanted to go that route. And 20 is 2 times 2 times 5, if I wanted to prime factor it. I just happen to know that one in my head. You don't, I don't care, whatever. You could reduce both components by 5, would you agree? In the end, 3 times 1, because the 5 over the 5 reduces to a 1. 5 divided by 5 is the same as 1 divided by 1. Your numerator is 3. Your denominator is 2 times 2 times 1, which is 4, yes? Okay, here's the first one. Now, the next thing I'm going to do is throw letters at you. What if there are variable components to these things? And this is still part of example 2. There are variables, you can still do the same thing. 16 times x times y over 18 times x. Now, where letters match one another, they are, you can reduce them out. And not all of you are going to do this the way I'm showing you. Some of you are going to do it in your head. Some of you are going to say, I can reduce both of these by 2. I know that. But just to prove it, I'm going to prime factor the top because I can do it in my head. If you can't, it's fine. 2 times 2 is 4, times 2 is 8, times 2 is 16, times x times y. The bottom is going to be 2 times 3 times 3 times x. Where do we have a match? A pair of 2's, any pair will do, and a pair of x's. So what is left in the numerator? 2 times 2 times 2 times y, which is what? And the bottom? 9x. 9, the x has disappeared. Yes, you're right. When there is no longer anything other than a 1 shared by the numerator and the denominator, you know you are completely simplified. If I left it with the x's in there, you would say, well, x divided by x, those two can reduce one another by x, by dividing out the x. That would not be completely simplified. Now let's just say this was a negative. Whether they floated the negative sign here, here, or here. All that means is the quotient of this entire thing is negative, so that just transfers right along with it. You don't have to worry about trying to divide out the negative or somehow change the sign. If this fraction is negative, then so is the simplified form. Okay, that's example 2. We're going to go back to exponents for a little bit. Nobody's favorite. This rule is that rule that keeps bothering us. When you divide exponents with the same base, you merely subtract the exponents. And that's what I've taught you up to this point. But there is actually another way of looking at it. And some of you might like this method better. Some of you might not. Okay, so here we are at example 3. x8 over x4. Okay. If I prime factored this out, which is going to be extremely annoying, I'll draw 8 x's on the top. 1, 2, 3, 4, 5, 6, 7, 8, and 4 on the bottom. Okay? Which means 4 pairs cancel out. So the bottoms all became 1s because x divided by x is 1. Any number divided by itself is 1. And the ones on the top that canceled with it became 1. Which means my numerator is x times 1, 1, 1 times x times 1, 1, which is x to the 4th, right? The denominator is 1. You don't have to write over 1. If you do, it's fine, but you don't have to. This process is the same as saying x 8 minus 4, which is x8. Where it gets tricky is the next version that I'm going to show you. The next version is what if it looks like this. And I'm going to do one that's smaller. I can still use the same process. There will be 2 p's on the top and 6 on the bottom. How many pairs of the letter P will cancel? Ugh. What is my numerator now? 1 times 1, which is what? And my denominator is 1 times 1, p to the 4th. I'm not even going to say that 4 times. Yep. 1. Well, look at what's in the top. 1 times 1. So there's your numerator. Bottom. 1 times 1 times p times p times p times p. So it is 1 is your numerator, p to the 4th is your denominator. 1 over p to the 4th.
Favorite hardline, can you go to the office, please?
This lends itself to a rule that it might click for some of you. If the numerator is bigger than the denominator's exponent, then the difference stays in the numerator. Okay? If the exponent in the denominator is larger than the numerator, then the difference resides in the denominator. This is actually listed in the middle of page 190 in the gray box. That is entitled Rule of Exponent for Division. I feel like once you recognize that if they're the same base, the bigger exponent, that's where the difference goes. I feel like that's an easier method than thinking of it the way it's been described in the past. There is a third component, and that's what if they match. Well, then Q, Q, Q cancels out Q, 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 and the answer is 1. And this can get intermingled, by the way, into more things than just those letters. Take, for example, 6x cubed, or squared, you know what, let's make it cubed, over 3x squared. Okay? Now what I've done is I've mixed what we did in the first exercise with what we're doing here now in the third. I've mixed it a little bit more. The 6 and the 3 reduce by a factor of 3, right? The numerator becomes a 2, the denominator becomes a 1 as far as the numeral is concerned. Then the x3 and the x2, that's like saying xxx and 2x's, right? 2 pairs of x's cancel out, leaving you with 1s where those were. 1 times x moves into the denominator. 1 times 1 moves into the, 1 times x moves into the numerator. Another 1 in the denominator. So in the end, you could tell me the answer is 2x and you'd be correct. Okay, and that is it. Greatest common factor again. Guys, example 4 is just a little bit more of example 3. So if you want to keep practicing, look over example 4. Example 3 is the same thing. Example number 5. We're just continuing to do what we've been doing so far, only with more difficult. Finding the greatest common factor of 2 or more monomials involves finding common or shared factors of each. So here's what I mean by that. And I don't know if I've showed you guys this yet or not. I want to try a couple. Have we done this already? Like this year? Or is this last year? Okay. I feel like we just did this. We're going to find the greatest common factor of these two things. And when you do that, what you're finding is what the common or shared factors are of each one. First thing you're going to want to do is prime factor both things. Specifically, start with the numbers. Ignore the variables for now. 21 is just 3 times 7, isn't it? Yeah. So numerically, 21's prime factorization is 3 times 7, recopy x cubed y. Just recopy that variable portion. Let's do 6. 6 is 2, 3, right? 2 times 3 times x6 times y cubed. Just bring the variable portion down. Numerically, what do they share exactly? They both share a what? A 3. 3 times. Do they share any other numbers? Nope. 21 has a 7, but 6 doesn't. 6 has a 2, but 21 doesn't. Let's switch to the variables. X cubed is x times x times x. Would you agree with me? X to the 6th is 6 of them. Okay, they both do share x, but how many do they both share? He has 3, he has 6, but he only shares with this guy 3 of them, which means the shared x value is x cubed. Let's look at y. Y to the first is just y. Y to the third is y, y, y. I wonder why. So how many y's do they both have in common? 1. They only have 1. Which means the shared y component is y to the first. So the greatest common factor is a product of all the shared factors. Okay? Leave out anything that one has but the other one doesn't. Anything that one has but the other one doesn't is of no use to you. That takes a little bit of practice. Now let's look at one final thing from example 6. This shouldn't take real long. When they say in example 6 in the book, they say simplify, and they've got 35x cubed y z6 over 56 x5yz. You're basically doing the exact same thing that we did right here, which was simplify and reduce by pulling out, or simplify by pulling out anything shared. Just because the number is bigger in their example 6 doesn't make the process any different. Here's the one that I want you to do. Negative 24 x3 y 5 z. Now make sure you're all trying this. I know some of you have already checked out, but you shouldn't be. X, y squared z4. So numerically, and the whole thing is still going to end up with a negative floating out there. Don't let that negative sign that's there concern you. Just transfer it right over into your answer. First, let's prime factor the numbers. 24. 32. They're both divisible by 2. This will take a minute. 2, 6, 2, 3, 3, 1, right? There's 24. 2 times 2 is 4 times 2. Okay, so 2 times 2 times 2 times 3. Bring those to the table over here. 2 is 16. And if you don't want to do it this way, if you can just visually see that they both share an 8, that's fine. But I just want to show you that if you don't recognize that the greatest common factor is 8, then you can do it this way and find what you need. Wow, and this is 2 times 2 times 2 times 2 times 2, isn't it? 5 2s. So they both share that numerically, which means I can reduce both of these numbers by 8. If I divide 24 by 8, what will I get? Come on, folks. 24 by 8. 3. 32 by 8. Okay. Now you can go back to looking at your variables. X's, Y's, and Z's. That should be a Z, not a 7. So X3 and X, what's left and where does it live? X on the top, X on the bottom. What is left and where does it go? Numerator or denominator? X to the second in the numerator, because 2 of the X's disappeared, or one of the X's disappeared from both components. How about the Y's? Y5, Y2, what's left and where does it live? Yep. Z, Z4, what's left, where does it go? Yep. That is the end, final answer. Nothing else can be pulled out other than a 1. And this process is simply a more complex version of this one. That's all it was. A more complex version of that one that we did over there. So I'll leave it up there just a little bit longer, and then I'll let you guys get started.